So what we're going to introduce today, we're going to introduce the idea. Last time we looked at linear modeling. Today we're going to introduce the idea of exponential modeling, right? And what you'll actually find is we've already kind of done this. We did this actually kind of in the beginning of class when we talked about compound interest, right? So when we have linear modeling, right? When we have linear modeling, right? That was a situation where we are at some point. Let me draw a little graph just for demonstration purposes. We start off with some point. We go over by a fixed amount. We go up by a fixed amount. We get to the next point. We go over by a fixed amount. We go up by a fixed amount. We get to the next point. We go over by a fixed amount. We go up by a fixed amount. We get to the next point. This makes us a line, right? So it is linear, right? That's why this is a linear situation. And this we called our run. This we called our rise, right? And we said that our slope equaled our rise over our run. So basically we're adding something each time, right? We start here and we do plus this amount, plus that amount, plus this amount, plus that amount, plus this amount, plus that amount. Now, when we want to talk about this new concept, which again, once we start talking about you probably will say, oh, that looks familiar. When we want to talk about exponential modeling, right? In this scenario, we're not adding to get to the new amount. In this scenario, we are multiplying to get to the new amount, right? That's what we're doing in this scenario. So with linear modeling, we add repeatedly to get to the new amount. And with exponential modeling, we multiply repeatedly, right? To get to the next amount. To get to the next level, we have to multiply repeatedly. So what ends up happening, right? It ends up making our exponential situation not have a graph that looks like this. Our exponential situation ends up having a graph that looks more like this, where it's a curve. So if we pick any 2 points on the curve, the rise and the run between those 2 points will be different, right? So if we keep the same run, let me say that. If we go over by the same amount, the amount we go up by will be different. And we can actually see that. So if we start here, if we do a point on the graph at the same places, and then this last one is just kind of too far. Look how far we went up the first time. The first time, right, we went up this amount. Whereas between the first one and the second one, look how far we went up. We went up much further, right? Didn't we go up much further to get to the second dot, right? The amount that we changed increased a lot. Who remembers what that picture looked like? Like, where did we see this before? What kind of situation do we see this? Where in one scenario, we were increasing by a fixed amount, whereas in the other scenario, right, we were increasing by different amounts, right? Who remembers the comparison between those two things was called? Does anyone remember?
It was interest, simple interest and compound interest.
Yes. So simple interest and compound interest. And what we end up seeing is that linear modeling, right? If we wanted to model simple interest, it would be a linear model, And if we wanted to model compound interest, it would be an exponential model. So that's what's happening. We model it, right? One is linear and one is exponential. So it's like we're getting new terms to describe what is happening, to describe something, a phenomenon we had already observed that we already knew was happening, right? So exponential modeling is like compound interest, where each time we don't increase by a fixed amount, each time we increase by a multiple of the previous amount. So it's repeated multiplication. Now, what we end up getting, because it's repeated multiplication, well, let's show what we have for the linear example. For the linear example, we get, and I'll do it in red because we were doing it in red, we have y equals mx plus b as our standard equation. For the exponential scenario, it's a bit different. And the standard, and this is kind of like it's not the general form, but it's just like a simplified version of the general form. We will have something that looks like this: y equals a times r to the x power. A times r to the x power, where a is some principal or starting point, r, right, is some I'll call it a ratio of change. I'll call it a rate of, I'm just going to call it a rate of change for now. Right? It's the percentage rate of change. And again, remember, we need a scenario like this. We need something like 1 plus r. So if you remember back in our compound interest that we did back in the day, we were doing 1 plus our interest rate in the function. So if you look back at the functions, we had 1 plus the interest rate in those functions, right? And x would be the amount of times the amount grows. Right? Or the amount of cycles, pretty much. So if we're measuring in years, it could be in years. If we were measuring in months, it could be in months. If we were measuring in days, it could be the amount of days, right? It's a couple of different things that it could be. Now, in particular, I usually find it useful, and I'm not sure if we did this. Did we do an example with money where we said you could either get $20 million a month or something like that? Did we do that example in class? I feel like it was a different class I did that example with.
No.
No, I don't remember that.
Okay, so let's do an example really quickly and keep this thing that we just wrote in mind. Keep it in mind, right? So the example that we'll do really quickly is, let's say you get some rich benefactor, right? The person you're dating is filthy rich and they decide that they're going to support you financially, right? And they give you two options, right? They're a billionaire. Maybe they're Bill Gates or something like that. And they give you two options, or it's Jeff Bezos. Isn't Jeff Bezos recently divorced? And Jeff Bezos says you have two options. Either you can, I'll give you $20 million right, a month. He's going to do this for 2 years, for 1 year, right? $20 million a month for 1 year. Or the other option is you start with $1 and he'll double the amount of money you have every day for 1 month. $1 doubled every day for a month. So for 31 days. Right. So you can type in the little chat, which option would you take? Do you want the $20 million a month for a year, or do you want $1 doubled every day for 31 days? You can type it in the chat. You can say it, unmute yourself, say what you would like. Which option sounds better? Anybody? Which option sounds better? So Dion says the 20 million. 20 million. Anybody else? 20 million. 20 million. So y'all taking the 20 million. So Felicia said the $1 every day. Angelique said the 20 mil. Veronica said the 20 mil. Tempe said the 20 mil. Ashley said the 20 mil. Okay. So let's say how much money. Let's see how much money we would have. Catherine said the 20 mil too. So let's see how much money we would have with the $20 million a month, right? So it's $20 million a month for 1 year. That's actually a pretty simple calculation. Can somebody tell me how we should do that calculation? What should we do?
$12 times 20.
Which equals what? $240 million. That's pretty sweet, isn't it? It's a lot of money. So all of you people who wanted the 20 million, y'all get a sweet $240 million from your rich benefactor. Now let's see what I think it was only two of you. I think it was only two of you that said you would take the $1. I think Felicia said the $1 and Michelle said the $1 a day. So let's see what we end up with the $1 a day. So starting off, right, what I'll do is I'll do day 1, day 2, and I'll just do 3, 4, 5, 6, 7, 8, 9, and 10. So I'll zoom in here and I'll just make 3 columns showing what we have. So we start off with $1, right? That's what we start off with. Now after day 1, what do we get? Well, we double it. So we go to $2. Then we go to $4. Then we go to $8. Then we have $16. Then we have what? $32. Then we have $64. Then we have $128. Then we have $256. Then we have $512. And then on day 10 we have the grand total of 1,024. So we're only on day 10. We got to do this 3 times, right, to get to day 31, right? Because it's for 31 days. Does anyone want to? Either of you, Michelle or Felicia, do y'all want to switch your answer? You gonna change your answer? Or are you sticking with your answer? Do you think it's gonna go up to be enough, or are you sticking with your answer, Felicia? I don't know if that's yes, I'm sticking, or yes, I'm changing. Oh, you changed it to the 20 million. Okay. What about you, Michelle? Are you sticking with the $1 a day, or are you changing to the 20 million? We can get you on mute. You still on mute? Nope, still on mute. Okay, type it in the chat. There we go.
Okay, Professor Lane, she said she'll take the $1 a day, but this also Barbara too. I take the 20 million.
You taking the 20 million?
Yeah.
Gotcha. Okay. So.
No, but Michelle's still stick with the $1. This is Barbara speaking.
Gotcha. So Barbara's taking the 20 million, but Michelle's still sticking to the. So it's only Michelle's the last holdout. So let's do another 10 days and see where we end up with. So we have 1024 times 2, and we get 2048 times 2, and we get 4096 times 2, 8192. Then we get 16384. Then we get 32768. Then we get 65536. Then we get 131072. Then we get 262144. Then we get 524288. And then we finally get to $1 million. But look at over here. They are at $240 million. Is there any way we are going to catch them? Doesn't seem like it, does it? So let's do another. Not at all, right? So let's do another. Let's do our last 10 days. Let's do our last 10. Well, we have 11 days. Let's do our last 11 days.
Hello. Hello?
Yeah.
Professor, this is Miss Pickett.
Yeah, I hear you. What's up, Miss Pickett?
Okay. I picked 20 million too. I didn't know how to unmute this.
Oh, okay. You
but
picked 20 million?
Yes.
Okay, gotcha.
All right. Okay.
All right. So now we're at 1 million. Let's see. It doesn't seem like we'll catch, does it? So after the 1 million, I don't know where I went. After the 1 million, right? I'm just gonna round it off. So I'm gonna put 2 point.
We get the point. She's not going to catch up.
2.1 mil. Then we're at 4.2. I'm just rounding it. 2 million. Then we're at 8.4 million. Then we're at 1.7 million. Then we're at. You know, I've been doing this wrong. I need to go back.
Oh, wait, hold on. How you go from 8 million to 1 million?
We're at not 1 million, 16.8 million. I moved my decimal place to the wrong place. 16.8 million. Then we're at 33.5 million. Then we're at 67.1 million. Then we're at 134.2 million. Double that is 268.4 million. Wait a second. We're not even there yet. We're at 268 million. But on this side, what do you all have with the 20 million there? Y'all just got 240 million. So Michelle is looking like she got a good little bit of money right there. Right, so we're only at day 28, and we've already passed it. Let's see what's next. Well, next is 536.9 million, and then after that is 1.07 billion. Because 536 plus 536 is 1.07 billion. And then for day 31, the very last day, Michelle would end up with a grand total. I'll write the whole number out. This is how much money Michelle would have, or 2.15 billion dollars. Which is significantly, that's not just a little more, right? That's significantly more than what the rest of you all have with your measly $240 million. Michelle has $2.15 billion, right? So what happened there? In this case, we started with such a small amount. But how did we grow? We grew by what? 100% each time. Each time we increased by 100%. Right? Each time, every single time, we increased by 100%. Whereas here, we didn't increase by a percentage. What did we increase by? Here, we increased by a fixed amount, which is why it was just multiplication, because we just added 20 million. Every month, you just add 20 million. Whereas here, in this situation, every month, we multiply by 2, right? Every single month, we multiply by 2. So this gives us a very clear picture of what happens when we do exponential growth. Now, don't try to think that you could take $1 and go double it every day and end up with $2.15 billion, because you won't end up with $2.15 billion. It would actually be relatively almost impossible to do this, to actually do this in real life. I mean, you could maybe technically do it, but it would take you years and years. Like, you could probably double $1 every day for 10 days and end up with $1,024. You might even be able to go up to like $16,000. But once you get to $2.1 million, how are you going to make another $2.1 million in one day, right? So every time I do this example, right, every time I do this example for students, they're always like, I'm going to go home, I'm going to try that. I have $1, I'm going to try to double my dollar every day. It'll work for a little bit, but after a while, it'll be very difficult. Like, you won't have enough money, right, to be able to keep doubling it, right? But what this gives us is this actually gives us a very easy way to represent exponential situations. That's what this gives us. A very easy way to represent exponential situations. So what I want to do is I want to take this example, the second example with the $1 doubled every day, and I want us to like kind of make an equation for it to see what happens. So in that example, right, let's say we want to find at the end, let's say we want to find the amount at the end, and we'll just call the amount M. I'm going to call it, no, let's not use M because that's the slope. Let's use A, right? So we'll call the amount A. Uh-oh. No, I shouldn't use A because I used A up here. We'll just call it Y. That's what we'll do. We'll just call it Y. So Y is the amount at the end of whatever doubling or whatever it is that you're doing. So that's Y. Now, what are we doing to find Y? Well, we're starting off with $1, right? And after day 1, what do? We multiply by what?
By 2.
We multiply by 2. And then what do we do next? We multiply the next day. What do we multiply by? 2 again. And then the next day, what do we multiply by? 2 again. And then we multiply by what? 2 again. And we're just going to say dot, 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 dot. All right, that's what we'll just say. Because we keep doing that all the way till we get up to the number of times that we are actually going to double. All right, we keep doing it, doing it, doing it, and doing it, all the way up till we get to the number of times that we actually double. So what we can actually rewrite this as is Y equals, and it's going to be the $1 times 2. And what do we do with repeated multiplication? What do we do? So if we add a bunch of times, we can write the repeated addition as multiplication. But what do we write repeated multiplication as? What operation is repeated multiplication? Starts with an E.
Exponent.
Exponent.
An exponent, exactly. And what exponent are we going to raise it to? Well, we're going to raise it to whatever exponent for however many times we double it. So in this case, how many times did we double it? We doubled
31
it
days.
31 times. Right? So we'll raise it to the 31st power. What if we wanted to double it for 100 days? Well, we could do the same thing. We could say that Y is going to equal the $1 times 2 to the 100 power. If we wanted to do it for 5 days, we could say Y equals 1 times 2 to the 5th power. Right? So we have options in terms of how many days it is. But we could actually write it in a general way. We have Y equals 1 times 2, and we're going to raise it to a power. The power is going to be X. And the X is just the number of times it actually doubles. That's what X is going to be. The number of times it doubles, right? So X is the number of times it doubles. And if we look up here, it kind of looks similar to this thing right here, doesn't it? It looks similar. Y equals something times something raised to a power. See that? Y equals some starting point In our example, what was our starting point? In our example, our starting point was what? $1. So y equals the $1, which is our starting point, times some number r raised to a power. And what number r do we have raised to a power? We have 2 raised to the x power, where x is the number of times something doubles, and this 1, we have a 1 there, but this is really going to be the starting point. Now, the beautiful part about exponential growth, right? Because you may say, well, in this case it doubled. What if it grows by some different amount? What if it doesn't double each time? What if it grows by 50% each time? The beautiful part about exponential growth is that anytime we have exponential growth, doesn't matter what percent it grows by, there will be some regular period of time with which our total amount doubles. So our amount could grow by 5% every year. But there will be a time, and if it grows by 5% every year, it'll be about like every 12 or 13 years, no, every 14 years or so that our amount will double if it grows by 5% a year. Every 14 years, the amount that we have will double. So if we start with $2 and we're growing by 5% every year, it will take us 14 years about for us to have $4. And then if we grow by 5%, it'll take us another 14 years about, right, for us to have $8. So every time you have exponential growth or decay, it leads to a repeated doubling. So anytime you have, and in this case we're talking specifically about exponential growth, anytime you have exponential growth, right, it leads to some kind of repeated doubling. Anytime. Doesn't matter what you grow by. It will always lead to some kind of doubling. And if we know how many times we're going to double, right? To double something is just multiplying it by what? Doubling something is just multiplying it by 2, right? So if we know how many times it doubles, well, all we need to do is just multiply the initial amount by 2 that many times. So then what we end up with is y is going to equal the initial amount we start with. And I'm actually going to do a p for the initial amount that we start with because we were using p for the principal before when we did compound interest, right? So I'll use p times 2, and the power is going to be however many times we actually double. That's what the power is. However many times we double. Right? And this is what we are going to use as our simplified exponential growth formula. Simplified exponential growth formula. Right, that's what we're going to use as our simplified exponential growth formula. Now, let me ask you all another question. Let's say we have a lab, right? So we have some kind of lab. And in our lab, we are cultivating some kind of bacteria, right? Cultivating just means we're growing the bacteria, right? So we're growing some kind of bacteria. Actually, let's do a different example because I always think this example is a little abstract. Let's instead say we have a farm, right? And instead we are breeding rabbits. So we are breeding rabbits on our farm. And let's say we have some kind of rabbit cage, but our rabbit cage can only hold 100 rabbits max, right? That's how many rabbits our rabbit cage can hold. Now, here's the problem. So our rabbits double. We're just going to pretend the amount of rabbits we have doubles every day, right? So the amount of rabbits we have doubles every day. That's because they're breeding. They're doing what rabbits do, right? And they're breeding and they're making more little baby rabbits. So every day, the amount of rabbits that we have doubles. And after 10 days, right? After 10 days, we won't say, let's erase this. We don't know how many rabbits our thing holds. I'm going to erase that. We're not going to say it holds 100 rabbits. We'll just say we don't know. It can hold some number of rabbits. Some number of rabbits. And after 10 days, right, the cage is full. It doesn't really matter how many rabbits it holds. But after 10 days, the cage is full. The question is, on what day was the cage half full? Right, that's the question. So we have, was it half full on day 1, on day 2, day 3, day 4, day 5, day 6, day 7, day 8, day 9, or day 10. Day 10, it was full. Okay, so I'll use dark blue for full. So day 10, it was full. The question we want to know is, on which day was it half full? Day 1, 2, 3, 4. These are our options. Which day was it half full? It was completely full on day 10. Which day was it half full? So I need to hear some guesses from people. Or at least what you think. What do you think? So you can take it off mute. I need to hear some voices.
5.
On day 5?
Day 4.
So day 5, I'm hearing day 5. I'm going to mark up which days I'm hearing. So I'm hearing day 5. I heard somebody say day 4. I think Dion said in the chat day 6. Anybody else have a guess? What day was it half full?
This is Pickett.
Mm-hmm.
I said day 6.
You say day 6?
Yes.
Somebody said day 9. Megan said day 9. Heard more day 5s, day 6s. We're going to double down on our day 6s. I see another day 4. I see one person said day 3. Day 5, more day 5s. So day 5 seems to make sense, right? 10 days it was full, so that means 5 days it was half full. It took 5 days for it to be half full, right? That makes sense to everybody, doesn't it? But let's remember one key thing. The one key thing we need to remember is this right here. The rabbits double every day. So if the rabbits double every day, right, then what's happening? When the rabbits double every day, if we go back 5 days, we won't be at half the point. We're going to be at way less than half. Let's go back up to our money situation, where our money was doubling every day. Let's see, how much money did we have on day 10? On day 10, we had 10,024, right? That's what we had on day 10. We had 1,024, not 10,024. Day 10, we had 1,024. When we go back to day 5, how much did we have? On day 5, we had $32, right? On day 5, we had $32. 32 is definitely not half of 1,024, right? If we want to find the day that it was actually half, all we need to go back to is just 1 day. If we go back 1 day, we get to 512, which is half of 10,024. So yes, it's day 9. If it doubles every day, all we need to do is go back 1 day to get to half. Right? That's all we need to do. Just go back 1 day. So here, the answer for the correct person, I think the correct person was Megan. Was that you, Megan, who got the correct answer?
Yes, it was.
So the answer is day 9. Day 9 is when we would have a half full cage of rabbits, right? Because day 10, that half full is going to double and it's going to give us full. When you double half full, you get to full. So in 1 day, you go up to full. Because again, with exponential growth, you are doubling and doubling and doubling over time. You are repeatedly doubling, right? That's what exponential growth is. You are repeatedly doubling. Now, there are a couple of things that I want us to do really, really quickly, and then we'll be done. This might take us another 15 minutes. So we had this equation here, which we said was our simplified exponential growth. I'm going to rewrite it down here. So we have y equals p times 2 to the x, right? Where we said x is, right, the number of times we double, right? And P is our starting point. So to be able to find out what amount you'll have after a certain amount of time, those are the only two things you need. All you need is the starting point and the number of times we double, right? So getting the starting point is pretty easy because in most cases, almost every problem is going to say we start with this much, right? So that's the starting point. It's really easy. So for the starting point, we get the starting point from the problem. Specifically, we get the starting point from the given portion of the problem. So from given, whatever the problem gives us, that's where we're going to get our starting point. Now, the only other thing that sometimes will cause us trouble is finding out the number of doublings. That's what I'm going to call it. Number of doublings. So number of times we double. I'm just going to call it a doubling. So the number of times we actually do double. That's the only other thing we need to figure out. And sometimes that won't always be readily apparent. Sometimes the number of times we double will not always be readily apparent. And sometimes we need to figure this out. So if the problem doesn't explicitly tell you, like how the money problem told us, the money problem explicitly told us, right, that we are doubling for 31 days, right? So that's what it explicitly said. $1 doubled every day for 31 days. Well, that's easy. But in some cases, we won't actually get that. So we need to figure this thing out, right? So in a lot of cases, what we will get is we will get what we call a doubling time. And we'll use the doubling time to figure out how many times we double, right? So we'll get a doubling time. So that's what I'm about to do now. I'm going to show us how we can figure this out. So to figure it out, step 1 is what is the doubling time? The doubling time is how long it takes to double. How long did it take our rabbits to double? Anybody?
1 day.
It took us 1 day for our rabbits to double, right? How long did it take our money to double in that example? It was 1 day again, right? So that's like the doubling time. Every day it doubles. Whatever period of time it takes for our amount to double, that is the doubling time. So in our rabbit example, it was every day, right? The second thing we need to do is convert our time period to the same units as our doubling time. So what we mean by this is, let's say for the money example, right? Let's say for the money example, right up here, instead of saying $1 doubled every day for 31 days, what if I had said $1 doubled every day for 1 month? Would you know that 1 month is 31 days? Well, I mean, it's 30 or 31 days, right? You'd probably ask, is it 31 days? Is the month going to be 31 days, or is the month going to be 30 days? So you're just converting it. What if I said $1 doubled every day for a year? Well, what do we need to do? A year is going to equal what? How many days? We need to convert 1 year into what? Days. So 1 year equals 365 days. Right? So that's us converting it from into the unit of our doubling time, because this is the unit that we want. Right? That's the unit that we want. Right? But we were given this unit here. So we need to write it in days, because then we can say if it's doubling every day and it doubles every day for 1 year, how many times will it double? It's going to double 365 times, because it doubles every single day, right? Think about doubling as like an action, like a thing happens, like a bell rings. If a bell rings every day, how many times will the bell ring in 1 year? The bell will ring 365 times in 1 year, right? So think about it in that way. If it rings every day, if it doubles every day, how many times will it double in a year? How many times will the bell ring in a year? It'll ring 365 times, right? Other cases might be, what if we had a situation where we were doubling every half hour, right? What if we were doubling every half hour, and I said that we are going to I'm gonna do every hour first, sorry, and then we'll do every half hour next. So if it's doubling every hour, and I said it's going to double for 2 days, right? What step 2 want us to do? It's doubling every hour, and it's doubling for 2 days. What do we need to do? Convert the time period to the same units as the doubling time. So we need to convert the 2 days into what unit? Hours. How many hours is 2 days?
48.
48 hours. Right. So it's not that, this part is not that complicated. We've done unit conversions already, but that's pretty much what we need to do. And then step 3 for us finding the number of doublings, the number of times it doubles, and this is the last step, is to divide the time period, and we're going to call the time period big T, right? Divide the time period big T by the doubling time, we'll call that little t. Right? Divide the time period by the doubling time, or basically we do T over big T over little t. Right? Big T is the time period, the amount of time that passes. Little t is the doubling time. And once we divide it, we get that big T over little t equals X, or the number of doublings. Right, which is what we were looking for. So that's once we do that, we have found what we are looking for by doing big T over little t. The time period divided by the doubling time. Right? So an example that I'll give, let's say we were doubling every let's say we were doubling every half hour. Right? If we were doubling every half hour, and let's say we'll do the same every 2 days. So let's say we're doubling every 2 days. Highlighter. So every 2 days we're doubling. It's every half hour. This is our example. We say how many times will it double? Well, to figure out how many times it will double, what do we need to do? Divide the time period by the doubling time. And to divide the time period by the doubling time, they need to be in the same unit. So I put every hour. None of y'all were going to say anything to me? Every half hour. Can't believe it. Y'all were just going to stay silent. Right? So we need to divide the time period by the doubling time to figure out how many times it doubles. So in this case, it'll be what? The 48 hours. And what's the doubling time? A half hour is how many hours? How many hours is a half hour?
You mean how many minutes?
Nope, how many hours? We know how many minutes it is. It's 30 minutes, but how many hours is it?
Well, wouldn't it be 48? I mean, because it's part of an hour?
No, it wouldn't be 48. We're asking how many hours is a half hour? 1.5. So 1 hour is 1 hour. A half hour is
0.5.
0.5 hours. Yes, so we're dividing this by 0.5 hours. Right, so 48 hours divided by 0.5 hours, and we get the number of doublings, right? And you'll see here that we actually don't have a unit for the number of doublings. So what's 48 divided by 0.5?
96.
96, right? So we have 96 doublings in that case. So in that situation, if something doubled every half hour for 48 hours, it would double 96 times, right? If it doubled every half hour for 2 days, it would double 96 times. So this is one method. No, well, this is the method for finding the second thing that we needed. What was the second thing that we needed? Second thing we needed was the number of doublings, right? How many times we actually double. A lot of times the problem will require us to calculate that out, just like what we just did following these 3 steps. What is the doubling time, right? Then we convert the time period to the same units as the doubling time. Then we divide the time period by the doubling time. Now, the only other thing that we may need to do, right? The only other thing we may need to do is in some cases, right, the problem may not explicitly tell us what the doubling time is. So in those cases, for us to find the doubling time, if the problem doesn't tell us, we can use what's called the rule of 70. The rule of 70. Now, the rule of 70 is a method for estimating the doubling time. Like, see how up here we have every day, every hour, blah, blah, blah. The rule of 70 is a method for estimating the doubling time. So with the rule of 70, right, because remember we said earlier, anytime you have exponential growth, it doesn't matter what percent it doubles by. It will always, what percent it increases by, it will always eventually double. Right? No matter what percentage it increases by, it will always eventually double, and it will double on a regular time period. So what the rule of 70 allows us to do, it allows us to take a percentage that an amount is growing by, right? And use that percentage to estimate the doubling time. And it's very simple what you do. So let's say an account this is our example for the rule of 70. Grows, and I'm sorry, let me say what we do. So to do the rule of 70, we just do 70 divided by the rate of growth. So let's say an account grows by 18% every month. And we want to estimate the doubling time. $13% every month. We want to estimate the doubling time. Well, we would just do it. We just take the 70, divide by 18, and we get an estimate for the doubling time. Now, it's important that when we do this divided by R, we just put that 18 directly in it. We don't turn the 18 into a decimal. It's just an estimate. So all we need to do is literally 70 divided by 18. And 70 divided by 18 will equal 3.89. And because this initial thing was 18% every month, right? The doubling time is also in months. So our doubling time is 3.89 months. So the reason why we don't change it into a decimal is we don't change it into a decimal just because it's kind of a crude estimate. People have done some math and they've just said when you divide 70, some people will do 72, some people will do 70, but it gives you an estimate. And it's something people use a lot in finances. But it's a situation where you just trust me. Just trust me that we don't turn it into a decimal. So when we're estimating, we just do divided by 18, the whole percentage, like the actual number, not turned into a decimal. So let me put a little note. Don't turn to decimal. So we don't want to turn it into a decimal. We just divide it straight away like that. Is that okay, Dion? Does that answer your question? I know it doesn't really answer your question, but yeah, that's the best answer I have. It's just an estimate. And that's just the way we do the estimate. So here's our doubling time here. 3.89 months. Now, once we know the doubling time, we can go back up here and we can go to step 2 and then go to step 3, right? So if we don't know the doubling time, we need to find the doubling time using, and what do we call this rule? The rule of 70. So we find the doubling time using the rule of 70. And once we find the doubling time using the rule of 70, then we can go back up and we can, we can go back up and go to step 2, go to step 3, etc. Anybody have questions about that part right there that we just did? Anybody have questions about what we just did?
No.
Somebody? Anybody else?
No.
Amanda, you got a question? I feel like you have a question. I don't know why, but that's what I feel like.
No, I'm good. Thank you.
Okay. Catherine, I don't know why I feel like you got a question too. You got a question?
No, I'm okay. Thank you.
Okay. Let me see. Who else normally be asking questions? I know you got a question, Carrington and Candace. I know one of y'all got a question.
No, I don't have a question.
Candace, what about you?
No, I'm good. Thank you.
Okay. Yeah, I targeted all of my normal question people. I'm trying to look and see who else be asking questions. Those usually be my main question people every single time. Okay. All right. So with that, that's pretty much all there is to it. Let's do one quick example. And then we'll be done. One quick example and then we'll be done. So I wanted to just talk through it with you all, so that you all could have that opportunity to ask questions, just because I'm going to be sending you all the final today. So I wanted to just be able to talk through it so you could, ask questions and we could do an example. Because this will be on the final. What we do right now will be on the final.
But with the final, you're also sending the video for this class, right?
Yes.
Okay.
Yes. When we finish the recording, then when I finish this recording, I'm gonna talk I might just send the slides, because I think I might want to just limit what's on the final to literally what we did right now today. So I might limit it and not do the entire all of the slides. So let's do an example really quickly. So with our example, so we notice bacteria in a lab, and it's growing at a constant rate hold on, I don't know why I want to erase. It's growing at a constant rate of 60% every minute, right? It's going at a constant rate of 60% every minute. If we start with one bacteria, I think it's bacterium maybe. If we start with one, how many will we have? Let's not start with one. Instead, let's start with 7. How many will we have in a half hour? So what do we always start with when we do one of these problems? We always start with what? Find.
Fine.
Always. Every single time, you just start with the find. Every single time. So we start with the find. Right? And what are we trying to find? The amount of bacteria after a half hour. That's what we're trying to find, the amount of bacteria after a half hour. Let's do our given. What information does the problem give us that's important? Well, the first thing the problem's giving us that's important is what? This thing right here. We'll look at it. What does it say?
The principal.
Okay, so what would the principal be in this case?
7.
Because that's what we're starting with, right? So the problem tells us what we're starting with. So P equals 7 bacteria. Or our starting point is 7 bacteria. What else does the problem tell us?
A percentage.
Yes, and what's this say? 60% every minute.
Every minute. Yeah.
Let's do that in a different color. It tells us 60% every minute. So we're just gonna write that 60% every minute. And then there's another thing that the problem is giving us.
For a half hour.
Half hour.
Exactly. So the half hour part, because the half hour tells us how much time is passing. That's what the half hour part tells us. So all right, now we can go down to the solution. So we have our given. Now for our solution, the way we're going to structure is we're just going to look at these two things that we need to find. So we already know our starting point, and then next we need to find the number of doublings. So our starting point is what? I'm sorry, let's actually write the equation down first. Y equals P times 2 to the X. Let's write that down.
Is it right to use 2?
Yes.
Okay.
So there are a couple of different ways that we could do this, but yes, the way that I'm showing you, yes, it's right to use 2. We're always going to use 2 because we're going to do it from a perspective of exponential growth leading to something doubling. That's the perspective that we're doing it. Now, so there's what we have. Now we need to do the two things. First, we're going to do our starting point. What's our starting point? We already said it. 7.
7.
Right? And now we need the number of doublings, and we need to figure this out. Right? But this is going to equal our X, which is going to equal big T over little t, which equals the time period divided by the doubling time. And that's what equals the time period divided by the doubling time. Now if we go up here, we can see our 3 steps. So first, what is the doubling time? Do we know the doubling time? Let's go down here. No, we don't. Because what do we have? That it grows by 60% every minute. But that's not a doubling time. Right? That's a percentage, a growth percentage, not a doubling time. We need a doubling time. So step 1 is going to be to find out the doubling time. And what do we need to use to find out the doubling time when we have a percentage? We use the rule.
Rule of 70.
The rule of 70. Very good. So let's use the rule of 70. So our doubling time, little t, is going to equal what? 70 divided by what?
60.
Divided by 60. Very good. So 70 divided by 60. And what's 70 divided by 60? Somebody do it in their calculator.
1.16.
So let's round that 6 off to a 7 because it's 1.1666666. So our doubling time will be 1.17 minutes. So every 1.17 minutes, our amount is going to double. Every 1.17 minutes, our amount will double. And then, so now we know the doubling time. What's the next thing? Convert time period to same units as doubling time. Our doubling time is in what unit? What units are our doubling time in?
Minutes.
Minutes. So our time period is in what? It's hours. So we need to do our time period in what? Minutes. So our time period is a big T, and that's going to equal what? It's a half hour. So it's 0.5 hours, which equals 30 minutes. And then step 3 is divide time period T by the doubling time. So we do big T over little t. So big T divided by little t equals 30 minutes divided by 1.17 minutes, right? The minutes cancel. And we end up with what? Somebody do that. 30 divided by 1.17.
25.64.
25.64. So it's going to double 25.64 times. And then all we need to do from here, right? All we need to do from here is plug it all back into our initial thing. Plug it back into this. So let's plug it all back in. We have y, which is what we're trying to find, equals p. What was p? P was the starting point. So it's 7 times. I'm actually going to write this in a different color to kind of make it stick out. So we have y equals p was the starting point, which is 7 times 2. That kind of looks like a plus. Times 2. And what power are you raising the 2 to? 2 to the 25.64 power. Right? And now you just do that exponent in your calculator like you would do any other exponent. Right? Just put the exponent in your calculator. Remember, PEMDAS. So we need to do the exponent first, and then we can do the multiplication. So do 2 to the 25.64 power times 7. So what I got was this. I got 3, 6, 6, 0, 2, 1, 9, 4, 8.7. So that is 366,021,948.7. But as we know, big numbers are a little bit unwieldy. So I'm going to write this in scientific notation to make it a little easier. I'm going to move it over. Count 1, 2, 3, 4, 5, 6, 7, 8. Because this is where I want to move my decimal point to. And I moved it over 8 spaces, so I have 3.66 times 10 to the, and I moved it to the left, so am I going up or down?
Up.
Up. 10 to the 8. So this is my final answer. This is the answer. 3.66 times 10 to the 8. Okay. That was relatively simple. I mean, it was a little tedious, and I feel like I moved a little bit slow, and you all were like, God, Professor, can you just move a little faster? But it's a very, very straightforward, simple process. It's not a super complicated process. All right. So with that, if there are no other questions, I'm going to go ahead and stop the recording. Unless anybody has a question. Anybody have a question?